Hello, everyone. We're going to get started with our webinar on Scalable CI and binary generation using Spack, GitLab, and AWS. My name is Lisa Avila. I'm one of the founders and the CEO of Kitware. I'll be speaking to you for just a few minutes to welcome you and give you a brief introduction to Kitware. And then I'm going to turn the mic over to our speakers for today. We have John Parent, Zack Galbreath, and Ryan Krattiger. We'll be pausing throughout the presentation to answer questions. So if you do have any questions, you'll see in the upper right corner, or maybe somewhere else if you're using one of the apps, there's a spot with a little speech bubble with a question mark in it. So if you click on that, it'll break open the question panel. So type your question in there and we'll answer it throughout the webinar. We'll also have time at the end to answer any final questions that you might have. We are also going to send out a copy of these slides to everybody probably tomorrow morning. So don't worry about writing things down or trying to screenshot the slides. We'll send you a copy of them. So let me tell you a little bit about Kitware. We are a software and AI research and development company. We have about 200 employees across our offices here in the US and over in Europe. We've been around since 1998. We are committed to open source and open science, and hopefully that passion comes through in this presentation. And we're proud to be a 100% employee-owned company. We're also a highly collaborative company. We work with many academic, government, and commercial partners on some very large-scale research projects, and then we like to take the results of those when we can and share it with the world through open source. We provide training, support, and commercial research and development services around those open source platforms to support those communities. And our primary focus areas for our research is in healthcare and life sciences, energy and manufacturing, and defense and intelligence. We are most known for our open source platforms, and we build vibrant communities around these platforms. These are some of our top open source projects, and many of these have been going strong for more than 2 decades. And so with that, I'm going to remind you again that questions go in the little question bubble. Type them in there. We'll answer them throughout the presentation. And at this point, I'm going to turn it over to John.
Hi, everyone. Like Lisa said, I'm John. I'm a developer here at Kitware, and I'll be walking you through just a very brief introduction into Spack, what Spack is, what positions Spack as unique in the package manager space, and then I'll be handing off to Zack for a little more detail on the scalable AI, CI. So Spack, what is it? Spack is a package manager. We like to think of it as a flexible, developer-forward package manager. It was originally developed for HPC use cases and has since been expanded to cover nearly every discipline of software development and supports all major platforms. It brings its trademark flexibility from the HPC world to developers everywhere. A package manager, for those of you who are unfamiliar with the general concept, is pretty well named. It is responsible for managing packages. It sits on top of existing infrastructure designed to build and install software and abstracts that away, so users only need to consider what it is what they need and not how to go about obtaining that or installing it. Spack is unique with a number of respects, but perhaps the most significantly are its configurability, flexibility, and developer-forward approach to package and system management. So what do we mean by developer-forward? Spack realizes that its role is not just to install packages. A lot of other package managers might stop at, we have installed your software, and that's great. Spack takes its role one step further and actually helps you manage the software on your system and integrate it into your development workflows. So one of Spack's primary unique features is its spec syntax. Its spec syntax is expressive and flexible. As you can see, very basically, we can have a basic expression of, I would like to install HDF5. Spack takes it one step further, fairly common, by expressing a version as well. Additionally, we can express a compiler and that compiler's version, further constraining the spec we want to install. We can take it an additional step further by specifying other build options and requirements for our build. We can take it a step further still by specifying actual C++ flags to be used on the compile lines. Spack additionally, having from provenance in HPC use cases, is able to target incredibly niche microarchitectures. So Spack allows you to set that from the spec syntax as well. And further, Spack has the capacity to arbitrarily specify all of these same constraints and requirements for all of the dependencies of a given package when expressing the spec that you are interested in installing. As you can see, Spack has an incredibly expressive and powerful spec syntax that allows you to effectively arbitrarily express and model exactly what you would like installed in your given system or environment. Each expression is a spec for a particular configuration, and each clause adds a constraint to that spec. Constraints are optional. They can range from the very basic HDF5 example at the top to the larger, longer, more complex example all the way at the bottom. And spec syntax is recursive, which means you have full control over your build space. So Spack has that great expressive spec language. How do we take that one step further and actually use that to produce some kind of output? Well, Spack produces, we go through a process called concretization or dependency resolution, which fills in the missing configuration details that were left out of the spec syntax or spec expression. So we take our fairly verbose spec, we're taking MPI leaks with a dependency on call path with all of these constraints on call path, and then an additional dependency on libelf with an additional constraint on libelf. Spack takes that, normalizes it into a DAG, or directed acyclic graph, representing the dependencies of your primary package and the additional constraints that you've specified on the command line. At this point, we have abstract specs. However, they've normalized and introduced some dependencies that perhaps you didn't directly express that Spack understands. We take that one step further and perform concretization or dependency resolution and basically resolve to concrete expressions of each spec in your dependency graph. This allows Spack to take your abstract expression of what you would like to have and produce something concrete that it can actually use to install. Further, Spack can now store that in either a YAML or a JSON file or a hash, and that allows Spack to provide detailed provenance about each package and how it was created, and store that alongside the installation of each package, allowing for you to call back to exactly how you got to that state and install that package. Further, Spack's approach to concretization allows for a significant degree of optimization. Spack allows the significant reduction of build overhead by reducing the amount of specs that are rebuilt in iterative builds. So if you were interested in producing a build for HDF5, typically you might reinstall every dependency of HDF5. However, Spack can see that iterative runs of installations might produce dependencies on identical specs. And by performing its concretization, Spack is able to determine which of these specs can be effectively reused for a given build and are compatible with the constraints applied on the command line, and can significantly reduce the number of packages you need to build, saving you time and effort. Further, Spack is incredibly combinatorial. So here we see just a generic dependency graph for Python. It's fairly complicated, a lot of dependencies and a lot of edges, a lot of dependencies of dependencies. However, Spack is able to produce a fairly simplistic installation layout for this fairly complex combinatorial expression because each unique dependency graph is a unique configuration, meaning 60 versions of the same library is fine, or one version of the same library can be reused for n number of dependency graphs. The root of each config has a unique directory. This allows Spack to effectively silo incompatible versions and limit them to only the specs which have been constrained to require them. Spack also uses a hash of the entire acyclic graph, or DAG, which is appended to each prefix, so you can track exactly which spec you produced with a given concretization. And installed packages know where their dependencies live. Spack uses embedded rpaths and binaries, no need for LD library path. Things work exactly the way that you built them and exactly the way you expect them to. Further, and Spack also exposes, and this is where, when I say Spack is a developer or package manager, this is kind of where this comes out. Spack exposes each packages via environments, either with a Spack YAML file or using the Spack load command. Basically, Spack drops the information required to consume all of the packages you've specified in your load command or environment into the environment exactly as you need to consume them. So you can effectively consume Spack packages transparently as if you installed them by hand on your system without any additional configuration or consideration from your own project. Basically, you can consume them exactly as you've built them and exactly as is. That wraps up the basic Spack intro. At this point, I will hand things over to Zack.
Thanks, John. I'm going to talk a bit more about what we've done building on top of Spack with regards to continuous integration. So at a high level, talking about what continuous integration is, the idea behind it is that you want to make relatively small incremental changes to your software project and have some automated systems in place to run tests to make sure that you don't accidentally introduce bugs or break important functionality. So as John just did a great job of explaining, Spack is a package manager. So the important features that we want to protect in Spack are our ability to install packages, right? We have some numbers on this slide here. Spack has just about 8,000 package recipes built into Spack that's separate from any user-defined Spack packages that live out there in the wild. And this isn't considering variants and different operating systems and different compilers. So you can see that this is a real combinatorial explosion of possible types of packages that we can build. So at least right now, it's pretty intractable to imagine building every single possible package that Spack could install, particularly because, as John just pointed out, these packages don't live in isolation, right? There's dependency information between them. So what we do in Spack CI is we have sets of packages that are important for the use cases for high performance computing and for other users that we really want to make sure keep working as people make gradual improvements to Spack. So as a side effect of the CI infrastructure that we've built, we are also populating binary mirrors with pre-built packages. These get reused in CI so we don't waste time or electricity rebuilding the same stuff over and over. It also is a benefit to our users because now they can download pre-built packages from our binary mirrors instead of having to rebuild everything from source all the time. Again, some numbers. So out of those 8,000 built-in packages, we are almost up to building 1,000 of them in our automated CI process. The amount of work that's actually done in CI changes from week to week because this is all driven by developer activity, but on average, it's about 100,000 rebuild jobs per week. And again, this isn't set in stone. The list of packages that are protected in our CI infrastructure is something that we are eager to expand over time. Eventually, wouldn't it be cool if we were actually building every single one of these 8,000 packages? Again, maybe we wouldn't have every different variant or every different C++ flag, every possible different build, but nonetheless, we are trying to grow that space of the number of packages that are protected by Spack CI infrastructure. So we're going to walk through the various components that we use to achieve, that we've used to build the Spack CI infrastructure. The first one that I'm going to mention is GitLab CI. If you're not familiar with GitLab, it's a version control system similar to GitHub. It's both hosted in the cloud at gitlab.com. It's also it's an open source web application that you can run yourself as a self-hosted system. There's some key terminology that's important when we're talking about GitLab CI offering before I talk more about why we chose this tool that it's worth going over. So what GitLab CI refers to as a job is really like the atomic unit of automated building and testing. It's performing some task. And that's vague because it's up to you as the project maintainer of defining what these jobs are meant to do. Skipping over artifacts for a second, talking about pipelines, that is a graph of jobs. So when you propose a change to your software project, it can kick off a number of jobs and there's dependency information between them. A typical example of a CI pipeline would be build, then test, then deploy, would be an example of a simple pipeline in GitLab CI. Going back to artifacts, those are files that get generated by your CI jobs that can propagate between jobs. So if you produce some result in an early job and you want to be able to make use of that result later on, that should be used as an artifact in the GitLab CI terminology. A concrete example of that would be you might build an executable during a build job, and then the subsequent test job, you actually be able to want to run it against some input data to make sure it behaves correctly. So that executable that you built in the build job would be an artifact that is then passed down in your pipeline to your test jobs. Runners are the, it's a process that is what's actually responsible for running your jobs in GitLab CI. You'll see examples of how we do this with Spack, where we have runners that live both in the cloud, running on AWS, and also running on on-premises hardware. And then finally, there's this concept of tags, which is how GitLab controls scheduling jobs to run on specific runners. These are just arbitrary string labels that you can apply to a job in a runner, and then GitLab makes sure that the jobs get scheduled to run on a correct runner. For an example, let's say you have a job that you want to run on Mac OS, and then You also want to make sure that that particular testing host has CUDA installed. You could apply tags, Mac OS, and CUDA to your job. And then GitLab would make sure that that job can only be performed on a runner that also advertises those corresponding tags. I'm going to just show a quick example of what GitLab CI syntax looks like. So this gray box down here, this is an example of the type of thing that you would write in your project to define a GitLab CI pipeline. This sort of lower level indentation is how you define a job. So here we have a build job, and you can see all it's doing is just echoing out a string, right? Then we have a test job. We're saying that's in a test stage, and then that echoes something else out. We have another test job, which also prints stuff, but takes longer and sleeps for a little bit. And then finally, we have a deploy job and a deploy stage. What this results in is a GitLab CI pipeline, which looks like this, where you have a build job in the build stage, the results of which get fed into the test job. There's two jobs in this stage of your pipeline. And then finally, you have your deploy job after that. So just showing a simple sort of hello world example of writing a GitLab CI YAML file and what the resulting pipeline ends up looking like. So the reason we selected GitLab CI for Spack, it has a feature that's very important for us that the other sort of options like GitHub Actions or Jenkins weren't as powerful. And this concept is what's referred to as dynamic child pipelines. What that means is we have a job in GitLab, which will then generate a GitLab CI YAML file dynamically, and that is used by a subsequent job to dynamically create another pipeline on the fly. This is important for us in Spack CI. Again, the concept of incremental builds, of not wasting time rebuilding the same stuff over and over. So at a high level, what we use this feature for is to check what packages are already up to date and don't need to be rebuilt, and then schedule a downstream pipeline that only rebuilds the stuff that has changed. Here's, again, the sort of simple contrived example of what dynamic child pipelines look like in GitLab CI and how to define them. You'll have one job. You can see it's just running some script to generate a GitLab CI YAML file, and then it provides that generated file as an artifact. You have a subsequent job. This is what is called a trigger job. This is what's going to be responsible for actually creating that dynamic child pipeline. It includes the artifact from the previous job. And that's really all there is to it as far as the syntax of triggering dynamic child pipelines. For a maybe more interesting example, this is an example of Spack CI actually running. This is just a pipeline from a couple days ago. You can see at a top level, we have a whole bunch of generate jobs. These are all generating downstream pipelines, okay? And then you can click through and look at one. And you can see here for this particular run of this particular E4S stack, you can see we've skipped a whole bunch of work here. And you can tell that because we're starting at stage 11. So we skipped stages 1 through 10. All of those low-level dependencies were already up to date, so we don't need to rebuild them again. Okay, the next component that I'm going to talk about that is part of the larger puzzle of how we've put together the CI infrastructure is a tool called Karpenter, which allows us to make use of cloud-based builders in a cost-effective manner. So Karpenter is what's called an autoscaler, which is specifically tailored to be very effective to use on AWS, Amazon Web Services. The problem that autoscaling helps us solve is this goal that I have outlined here. We want to maximize throughput, meaning run as many of these CI jobs as quickly as possible, while at the same time minimizing cost. So what an autoscaler does is it automatically provisions or tears down resources in the cloud for you in response to demand. There's some other sort of prerequisite concepts that are helpful to understand here that are unfortunately outside of the scope of this brief talk today. So this is all running in a Kubernetes cluster. We'll come back to that in a second. Ultimately, all of our CI jobs are running inside of Docker containers. A container is a self-contained application that's loosely decoupled or loosely isolated from the host environment that it's running on. Kubernetes is orchestration software that helps you solve the problem of scheduling containers to run. Basically, you provide a set of compute resources and a set of jobs or work that you want to perform on those. And Kubernetes handles scheduling what should run where for you. As Lisa said at the onset, you're all going to get a copy of these slides. I have a link at the bottom of the slide that I think does a good job of providing a gentle introduction of these terms and kind of the reason why they exist. Anyways, Karpenter is an autoscaler that is actually created by AWS. The features that we really like about it are that they make it very easy to define what they refer to as node pool. So what this means is you define a number of constraints on the types of CPU or memory or whatever, basically the types of instances that you want to run your work on. Karpenter is also very handy because it automatically optimizes sort of based on two criteria: lowest cost, so you don't want to spend more money than you have to, but also minimizing the chance that your instances will be interrupted, so that try to make it likely that the work will actually complete. Next, I'm going to show a quick example of the types of configurations that we use, again, in real life for Spack. In this case, what we're looking at over here is our definition for the types of constraints we use for our Graviton 3 runner. So this is a ARM processor, fairly new and modern out of AWS. So this goes back to what John was talking about, how Spack understands microarchitectures and building packages for particular instruction sets. So we have some of our packages that are specifically tailored to build for this newer version of the ARM processors. So how do we define that? With a series of constraints. One, we say only build on ARM processors. Next, we say only build on these particular instance types, instance families from AWS. And then next, we have the size of the instance that we're willing to consider. And then finally, we have the availability zones where we want to be able to perform this work in. So you can see we have 3 different instance families, 11 different instance types, 4 different availability zones. If you do the math, that ends up with over 100 possible options of where this work could be performed. So manually trying to specify all of that information to AWS would be very painstaking and error prone. So the fact that Karpenter can take all of these constraints, consider them together as a whole, and then optimize based on, again, low cost and probability that the job will actually finish has really been a huge benefit to us. Okay, at this point, I will hand the mic over to Ryan and he'll talk more about another piece of the puzzle, which is our ability to cache and reuse binaries using Spack.
Hi. My name is Ryan Krattiger. I'm a developer at Kitware as well, working on the Spack project. So in this section, we're going to talk about binary caches and sort of how they're used after we've gone through the build farm and done all the work to compile and push these binaries up to the cloud or wherever they're being stored. So first, what is a build cache under the hood? So a build cache is a repository of pre-built binaries that can be hosted in one of 2 formats. So the first format that's available is a file system-like format that can be deployed on a local file system in AWS 3 or GCP Cloud Storage. The second format that's supported by Spack is a OCI registry, or Open Container Initiative registry. These are registries that you commonly see in the GitHub container registry. The container registry is available at gitlab.com or in the GitLab web service, Gway.io, Docker Hub, etc. And so the use cases where build caches are very useful are so in like a local build cache configuration, this can be very helpful if you have a lot of iteration building containers where you want to install packages for some workflow. Having a local build cache that can be mounted into your container during creation time, grab binaries that are already built and store binaries as they're being built. This can also be very helpful for accelerating development workflows. Additionally, for sharing binaries across allocations on HPC centers, as well as in the cloud-hosted context, as Zach was talking about before, which we use for publishing the binaries built by the Spack CI build farm and running the pipeline. So one of the really important things about build caches is we want to consume them. But in order to consume binaries, we also need to be able to trust that those binaries were built by a trusted provider. And to do this, we utilize the GPG signing infrastructure. In the Spack CI infrastructure, they use a two-part signing process, so where every builder node has its own GPG key, which it signs, and this is a intermediate key. Those get pushed up to the build cache, and then once all of CI is run, there's an additional signing step that pulls down all of the metadata that had been signed by the builders and repushes them with the reputational key. In order to be signed by the reputational key, it first has to be verified that it was built on a trusted runner, and then it was re-signed. In this way, there's one reputational key for all binaries in the Spack build cache. And so you can say, if I have binary metadata that is signed with this key, I know that it was verified by the Spack CI infrastructure. So in this next part, I'm going to just again do a quick overview of the entire Spack CI build farm and how that sort of works together now that we've sort of covered all of the components. So the Spack CI build farm is triggered and follows the Spack development that is hosted on GitHub. This is synchronized across a CI bridge, which will monitor for changes on the develop branch, release tags, snapshot tags, and pull request. Synchronize this work to our GitLab instance that's running and is connected to our Kubernetes cluster, as well as on-prem runners that support the CI workloads for Spack CI. They will all go off. They will build all of the binaries for all of the different stacks that Spack CI is building, and then push them to the S3 build cache store hosted at AWS. And so there are tons and tons of binaries that we produce from this. And in order to make it a little bit more consumable for users to search what is in the cache and see what's available to them, we have a website called cache.spack.io. And here's a screenshot of that. And if I jump over here, I can show the page here. This is the develop tag that we're building against. So this is the latest. This is a selection of binaries from the latest Spack that's running in CI. I've searched for ParaView here, and you can see we have 218 different binaries available for ParaView. And it's built under all of these different architectures, operating systems, compilers, and then each of these stacks listed here is providing unique recipes for ParaView. In order to get this binary, or get these binaries, there's instructions on the top of this page to add the mirror for the develop tag to your Spack instance and how to install the keys used for signing, the public part of the keys used for signing, to verify these binaries when they're installed. All right, so the next part here is going to be a demonstration of the workflow. And so this is a very much simplified version of what we're running in the Spack CI build farm. And is meant to be something that anybody can clone and fork and reproduce themselves and experiment with. So I had shown this picture before. Here we're only going to use the components inside of the green square here. We have a S3 build cache that I set up. I'm using the GitLab.com GitLab instance, and we're going to be using the free runners provided by GitLab.com to run jobs. I have the link here to the demo, and we'll do a quick walkthrough. So here's the project. There's a README in here that will take you through more of the details of how this demo is laid out and which files are available, as well as walk through on how to modify this project to run for your instance of S3 and GitLab. So here is just a quick or a very simplified version of a .GitLab CI YAML. This is the entry point that Zack had talked about earlier for running GitLab jobs. Here in the first job, we see we have a generate pipeline. This pipeline generates using Spack CI generate a pipeline.yaml, which is then consumed as a trigger for the build jobs section. The environment that we're using in this demo builds two packages, zlib and bzip2 with no debug using the GCC compiler. Here we have a simplified version of a CI config. And here we are running a rebuild for the build job, as well as cloning our custom version of Spack that we're going to use for this pipeline, and general runner configuration. And this is what it looks like. So you can see here we have a generate pipeline that runs, that spawns the trigger job. And then under the trigger job for build, we have all of the stages running and building the packages here. And at the very end, we rebuild the index. So this step here is very important, as this is telling the build cache to update its index to reflect the new binaries that were produced during the pipeline run. So let's take a look at the generate job log here. Here we run the CI generate, which runs the concretization step that John had talked about. Then goes through and searches all of the mirrors that are registered. In this case, there's one, and sees do any of the hashes concretized in this generate job exist in the mirror or not. As we can see here, none of these packages were found in the mirror, and so we have a full rebuild of the entire stack. And so just to demonstrate here, this is the last job that ran for bzip2. This is Spack installing all of our dependencies for this build job from the build cache, building bzip2, and then at the very end, we're pushing bzip2 back to the S3 build cache that we're using to store these binaries. And so that is all that I have for the demo. This is available on, again, GitLab.com in my public repository for anyone to fork and try out themselves.
Okay, thanks, Ryan. So yeah, again, as a high-level overview, testing, writing thorough end-to-end tests for package manager is tricky. Some of the important concepts I hope you'll take away here is the idea of caching pre-built results and being able to use them. The idea of auto-scaling can be very powerful if you're running workloads in the cloud. And the features that we had to build into Spack itself to make this possible. So Ryan provided a link to his demo, so that's probably a good, gentle introduction if you're interested in doing something like this. On this slide, again, as Lisa pointed out, Kitware wants things to be open source as much as possible, right? Spack's no exception. So Spack source code is open source. The Spack infrastructure repository is the actual YAML definitions of our Kubernetes cluster. So the example of our Karpenter configurations, that's in there, a whole bunch of other stuff. So if you're interested in how Kitware and Lawrence Livermore National Laboratory is using Kubernetes to achieve these workloads, that's in there. That being said, we're happy to chat more with you all if any of this is interesting or you think it might apply to your work that you're doing. So in general, the Spack Slack team is very active and a very helpful community. So that's slack.spack.io. The particular channel that I know I personally keep an eye on, and I know Ryan does as well, is CI and pipelines. So that's an appropriate place if you have questions about this sort of stuff. But that being said, the general channel is okay as well. It's not the type of Slack team where you're not allowed to talk in the general channel. That's totally fine as well. As far as collaborating with Kitware, we have a link here for advanced support. So if you're interested in working together, that's a great place to start. The types of work that we do is mostly centered around customization and support. And as much as possible, we love when we can work together to improve open source tools. So yeah, we'd love to be in touch with you. We hope this was interesting. And yeah, please feel free to ask questions if anything we covered today, you'd like more details about it.
And you can, as I said, we will be sending the slides out. You could respond to that if you have some questions that come up after this webinar ends. If you have any last minute questions, please send it through in that questions area. We want to thank you all for being with us this afternoon for this webinar, and we'll be sending the slides and the link to the recording in case you want to watch it again, or anybody can still go to our webinars page and get to that copy as well in the future if you want to point somebody else to it. We'd love to hear from you if you are using Spack and you have any suggestions for improvements or notes about how you're using it in your environment. We'd love to hear from you, so feel free to reach out. So thank you very much for attending today. Have a great day.